Yeah, very good. We're trying to find dy dx, and the first thing we do is stand for people when they come in. Hello, Miss Casper. Thank you. This is for charisma. It says 2:35. That's in 10 minutes. We better go really fast here. We're trying to find dy dx. Is this equation solved for y? No. Are we going to be able to solve it for y? I don't think so. If I were able to solve, if that were the only thing in there, that would still be when I solve for y a plus or minus. That's two equations. We don't want to work with two equations. Besides, there's another y over here, and liberating that guy by taking the log of it will trap that guy behind the log. So it's a good thing that we don't need to solve for y in order to find dy dx because we just do it how? Implicitly. Good. So showing that we're taking the derivative, either d dx colon or d dx of both sides. So now I have e to the blob, which of course is its own derivative, e to the blob, times the chain rule, parentheses, right? Parentheses, you're in that habit now? Parentheses. And it's going to be a product rule, so the parentheses are really important here. The derivative of x with respect to x is 1. Well, you could, yeah, times the natural log of the base. What's the natural log of e, though? 1. So that's the only one that you don't need to put the natural log of the base. You certainly could if you want to just be consistently thorough. So 1 times y plus x times the derivative of y with respect to x. So that takes care of the chain rule on the first term. Okay, that's this right here. And then plus the derivative of x squared is 2x times dx dx, which we don't need, minus y squared would be minus 2y to the first times dy dx, which we do need. And, of course, the derivative of 10 is what? 0. Now all we have to do is solve for dy dx. We got this guy over here that's already kind of expanded. He's liberated, but this guy in here is trapped. And if you try to liberate him by dividing every term on both sides by e to the xy, that's not going to be the best route there because you have another dy dx. If that were the only dy dx inside there, then dividing through by e to the xy might not be a bad thing to do. But what works every time is expanding it out. And that's what we have to do here. So you get y e to the xy plus x dy dx e to the xy, and then plus the 2x minus 2y dy dx equals 0. So it's not difficult at this point. It's just kind of painstaking. There's a lot of symbols to carry around. And now we have our dy dx terms on the same side, so we'll factor out the dy dx. And we're left with x times e to the xy minus 2y. And then the other two terms that are not underlined go to the other side, so I'll call it a negative 2x and a negative y e to the xy. Now from here, how are we allowed to factor it? Yeah. You can leave them on the other side, but you just try to be as efficient as possible. And now we just divide through by that entire blob, and you end up with negative 2x minus y e to the xy all over x e to the xy minus 2y. And that right there is not a bad final answer. Notice it still requires both x and y. So just because we can't solve for y doesn't mean we can't take the derivative and then solve for dy dx. Now, how many terms does that derivative have? 4. Good. 2 in the top, 2 in the bottom. Of the 4 terms, how many of them are negative? 3. That's 75% of the terms. That's a lot of negativity. Y'all like being around that much negativity? Heck no, me neither. And you know who else doesn't? College Board. So what they would probably do in a situation like this is something I would do. If you multiply by a clever form of 1, like negative 1 over negative 1, that's legal, right? And essentially, if you distribute it through, you're changing all the signs of all the terms. So you get positive 2x, much better, plus y e to the xy, much better. And at the bottom, the 2y becomes positive, bless you. So I'll put it in the front. I don't like to lead with a negative either. And we have x e to the xy. And so now 3 of the 4 terms are positive. That's equivalent. And if you would have actually collected your dy dx's on the right-hand side instead of the left, you would end up with this answer to start with. So if you're ever doing some kind of implicit differentiation and you get a quotient and you're trying to match it to a multiple choice answer, if the magnitudes of everything look right but all of your terms just seem to be the wrong sign, that's why. Just multiply by negative 1 over negative 1. But don't fear, don't fret, don't panic, right? Just Do your best and forget the rest, right? Tony Horton. Okay. Any questions on that? No. Oh, like if I'd given you an ordered pair to plug in, I would have to give you the ordered pair because there's both an X and a Y. You would just show it like this. Now, I have no idea if this point 1, 0 is actually a point on the graph. It could be just out in space, but that's how you would write it, and then you would carefully plug in a 1 for X and a 0 for Y. But I didn't do that here. Okay, sweet. Now, on example 9, we'll do the rest of these together. It says to find that. What is that? Second derivative, good, of y with respect to x for y equals this. Now, are we going to have to do this one implicitly? No, that one is explicitly solved for y as a function of x. That's good. But is there any way to go straight from y to y double prime? In general, no. So we're going to have to go through y single prime. Well, you can in certain circumstances. Like if I said y equals e to the x and I ask you to find the third derivative, what's it going to be? It's going to be itself, right? You went straight to the third derivative. Good. What if I tell you that y is equal to 5 and I ask you for y triple prime? You know it's going to be 0. What if I tell you it's 5x to the 57th power and I ask you to find the 58th derivative? 0, right? We've already talked about that kind of stuff. And you could do some of that with cosine and sine as well. But in general, unless it's a specific pattern that you recognize, it's a recursive process. To get to the fourth derivative, you have to find the third, which means you have to find the second, so on and so forth. So enough talking. Let's get at it. Now, do you have to put d dx here to show what you're doing for a function that's already explicitly solved for y? You do not have to. But if you would like to, certainly feel free. It's only required when you have implicit. Because when you take the derivative of y with respect to x, that tacitly shows what you're doing. But hey, have them both there. That's great. Now, the thing on the right-hand side is going to require the what rule? Starts with P, rhymes with product. Product, good. Product rule. So I'm not going to distribute. I'm just going to leave the 3 plus 2x as a single variable factor. So the derivative of 3 plus 2x is 2 times 5 to the negative 3x goes along for the ride. Plus the quantity 3 plus 2x goes along for the ride times the fun one. The one I got out of bed this morning to meet. The exponential one. What is the derivative of 5 to the blob? How about itself, right? Times the natural log of 5. Good. Times the chain rule, the derivative of negative 3x, which is negative 3. Negative 3. And how about this? Dot negative 3. Does that look good? No. Grr. Just put parentheses. I will. Yes, I will. And you might actually hear me. And you might not even be at school. Okay? Now, that's the first derivative. Should we just jump right in and take the second derivative, or is it worth kind of tidying up a bit? Yeah, let's tidy it up a little bit. Dy dx equals, let's see, the first one looks good. 2 times 5 to the negative 3x. But over here, I'm going to have a negative, let's do the positive 5, negative 3x first. That's going to be one factor. And then I'm left with a negative 3 natural log of 5 times 3 plus 2x. Now, if I'm going to take the second derivative, here's what I notice. I notice, first of all, that I can factor out a 5 to the negative 3x power. And that's typically going to be something you want to do. No, you can't combine the 2 and the 5 and call it 10. No, not unless they were both to the negative 3x power. So let's go ahead and factor out the 5 to the negative 3x. And here's where I like to go with the beefy brown brackets. Beefy brown. In the first term, I'm left with a 2, right? And notice in the second term, I'm just left with this, which is going to be plus all that. Now, I'm also going to distribute that so that I don't have to worry about having a constant times a variable. If I just expand it out, what's my first term going to be? Negative 3 ln 5 times 3 is negative 9, so it's minus 9 ln of 5. Good. And then this one's going to be negative 3 ln of 5 times 2, which is negative 6 ln of 5 times x. Now, you got to be careful here. That x is not part of the natural log. So I put parentheses around the x. And that's about as good as we can get. Now, notice if I go to the second derivative, it's going to be another product rule. I have the exponential piece and then the beefy brown piece. But look at the first two terms in the beefy brown piece. Do you see any variables in those two terms? In the 2 minus 9 ln of 5? No, those are numbers. So guess what their derivative is going to eventually be? 0. And notice that this last term, minus 6 ln of 5 times x, that's just a linear term, right? That's just a number times x. What would be the derivative of 10x? 10. So guess what the derivative of negative 6 ln of 5 times x is? Very good. Okay, so that's just kind of thinking before we start. And now we're ready to go. If you want to show that you're taking the derivative of both sides again, nothing wrong with putting a d dx colon again. It is a product rule. But now on the left side, I have d squared y over dx squared equals. No, if it's explicitly solved, you don't have to. And it was from the very beginning. In other words, going straight from y to dy dx shows that you're doing. All right, so on the right side, the derivative of 5 to the negative 3x is itself, once again, times the natural log of 5 times a negative 3. Times the beefy brown piece goes along for the ride. 2 minus 9 ln of 5 minus 6 ln of 5 parentheses x. If you forget the parentheses around the x and you write it after the 5, we're going to assume it's 5x inside the log. All right, so there's the ugly first term, plus now 5 to the negative 3x goes along for the ride, and we are left with the derivative of the beefy brown piece. So I'll use beefy brown. Negative 6 ln of 5. We've already kind of had that discussion. Yep. And we're done. In the next chapter, we're going to be using this stuff, and so that's when it's going to be important for us to really clean it up. And this one, I don't think it's worth cleaning up because it is kind of ugly. But do notice that in the two terms that you have there, you do have a common factor, once again, of the exponential piece. And you have a natural log of 5 that is common. And there's also a negative 3 factor that you could factor out if you really, really wanted to. But let's not and say that we did. Sound good? All right. Any questions on that one? See you, Charisma. Any questions on that one? All right, last one. Example 9 is over. Yeah, example 10 has this wonderful, handsome dude here. He is drinking milk, or he hasn't drinking milk yet. Maybe he's on the second glass. You never know. But he's enjoying the activity, whatever it is, and it involves milk. Okay, and he's dressed for the occasion, right? You dress up that nicely every time you have yourself a nice cold glass of milk. You should, because it does the body good. Now, let's look at this example. It says calculator permitted, but you know what? I'm going to hold off on the calculator until absolutely needed. So let's treat this problem as if it were either a free response without a calculator, and then we'll talk about what to do if you did have the calculator the whole time. Step 1 is going to involve reading, right? Bless you. If not, drinking a cold glass of milk to start off, but I don't have any milk with me. So a glass of cold milk or a cold glass of milk, the milk is cold, the glass not necessarily, right? But it could be a cold glass of cold milk. That would keep the milk colder longer. Anyway, it's taken out of the refrigerator, and it's left on the counter on a hot summer day. A hot summer day. I don't know. If it's inside and it's air conditioned, maybe the outside ambient temperature isn't even relevant, right? Anyway, you got the scenario. We're taking milk out of the refrigerator, setting it on the counter. We're just leaving it alone. What's going to happen to that glass of milk? Is it going to curdle right away? No, not immediately. It's going to gradually warm. Yeah, it's going to gradually warm. Its temperature F in degrees Fahrenheit after sitting on the counter for T minutes is given by this function. All right, so there's the Fahrenheit in degrees Fahrenheit as time is measured in minutes since the glass has been sitting on the counter. What's the parent function of that dude? The parent function. What types of functions are we dealing with in this section? Exponential. What's the exponential parent function? Y equals 0.98 to the teeth power. Yeah. Is that going to be exponential growth or decay? It is decay because the base is less than 1. So it starts off looking like this. But if we put that into standard transformation form, the negative 30 would be in the front times 0.98 to the teeth power, and the plus 72 would go at the back. What would the negative 30 do to the graph of the exponential decay function? It does two things. The 30 would be a vertical stretch by a factor of 30, makes the graph steeper. But what does the negative do? Reflects it across the x-axis. Remember, it's out in front, so your y values are changing. So now that makes it approaching the x-axis from underneath, and it's actually now an increasing function. And then what does the plus 72 do to it? Shifts it up. So let's go ahead and quickly sketch what it would look like. The horizontal asymptote would now be up here at 72, and the graph would look something like this. Okay, so that would be degrees Fahrenheit graphed against minutes. All right, sweet. Let's answer the questions. Part A, what is the temperature of the refrigerador? How are we going to use this equation to figure that out? Temperature of the refrigerator. What's that? The coefficient? Can we assume, and we do have to assume a couple of things, can we assume that the milk in the cold glass in the refrigerator will actually reach the temperature of the refrigerator if it's been in there long enough? Yeah, I mean, maybe it doesn't because the glass acts as a little bit of an insulator, and so does the air around it caused friction, but for the most part it should be. So can we also then assume that as soon as we take it out of the refrigerator, at that moment, I caught it, it should still be the same temperature of the refrigerator? Okay, so if we can find the temperature at T equals what? 0. That should give it to us. So I'm going to go ahead and plug it in right here where I can see, and then I'll slide it over there. So F of 0 is going to be 72 minus 0.98 to the 0th power. What is, 30, I forgot the 30. Oops, that's a big part of it. Let me slide that in there. Okay, what is 0.98 to the 0 power? 1. So we get 72 minus 30, which is what? 42 degrees Fahrenheit. That is the temperature of the refrigerator. Is that a good temperature for the refrigerator? Yeah, I mean, it might be actually a little bit warm for a refrigerator. Most refrigerators run between, that's hard to say. We just call them fridges now, right? Most fridges are kind of frigid inside. They're just above freezing, 34 to about 38. So, but 42 would be if you're like on energy saver mode, right? Or you don't have like a bunch of cottage cheese in there, which is already curdled. 42 is not bad. That's what it is in this problem. We're not going to argue with it. Maybe so, yeah. And it's a hot, sunny day, so it's working hard to keep up. Yeah, or maybe it's an old-timey fridge where they actually had to put an big old block of ice in the top. You know, it was before Yetis. You know, anyway, well, like Yeti ice coolers, but like real Yetis, like Yetis. They still existed. What is the temperature of the room? What is the temperature of the room? On a wall. 72? How do you know that? Yeah. Very good. If you look at the graph that we did, it's approaching the upper limit of growth, which is the horizontal asymptote, which is 72. What if you didn't know what the graph looked like? What could you do with this equation? F of t equals 72 minus 30 times 0.98 to the tth power. What could you do to analyze that to get the room temperature? Find the derivative where the slope is 0. Will the slope ever equal 0? It's approaching 0. What could you do? Could you assume that if you let the milk sitting out long enough? A huge number for t. Very good. How about this? How about we take the limit as t approaches infinity? Would that work? Now, would you want to be there at the end of infinity to drink that glass of milk? Heck yeah. That's like free cheese. What happens to 0.98 when you plug in an infinity to its exponent? If that's exponential decay, it goes to 0, doesn't it? And so if that goes to 0 times 30 goes to 0, you're left with 72 minus 0, which is, of course, 72 degrees. So that's how you can analyze it. Take the limit as t goes to infinity. And, of course, the graph is showing that as well. Now, someone last period said, if the milk is warming up, why is it warming up like that? Why can't we just start with an exponential growth function like that and say that this is the starting temperature of the refrigerator, which was 42? What would happen in that case? Yeah, the milk would get pretty hot. In fact, it would get infinitely hot. There would be fire. You thought like eating like a pizza roll or a Hot Pocket destroyed your mouth. Yeah, this would be like hot milk, right? Hot milk. This would not be like the milk you would drink to help you go to sleep, proverbially, right? A glass of warm milk, spicy milk. Yeah, this would be the milk that would kill you. This is dangerous milk. Okay? Not lukewarm. All right, the last part here, part C. How fast is the milk warming when it is first removed from the refrigerator? Explain the answer in a complete sentence. So if you come over here to our reasonable graph, right here at t equals 0 is when we removed it from the refrigerator. And so I want to know essentially what the slope of the tangent line is right there. I'm going to move it. What is the slope of the tangent line right there? That's going to require a little bit of, what's it called, the C word? Calculus. Good. So I want to find f prime of 0. That's what I'm interested in. But before I find f prime of 0, I need to find f prime of t, right? So let's do that together. We can see f of t up here at the top. What's the derivative of 72? 0. Nice. Minus 30 goes along for the ride. Times, what's the derivative of 0.98 to the tth power? Yes, itself, right? 0.98 to the tth power. Chain rule. Oh, no, you can't go 30 times t to the blob to the t minus first power. The power rule doesn't work. Why? Because this is exponential. So 72 goes to 0, negative 30 goes along for the ride. The derivative of any exponential function is itself times what? ln of the base, which is 0.98. Times the chain rule, the derivative of t with respect to t, which is just 1. So there's the derivative. Now let's plug in a 0, f prime of 0, and we get negative 30 times. And what happens to this middle factor here when we plug in a 0 for t? It becomes 1, okay? Very zen. The natural log of 0.98. Now, if this were truly a free response question and you did not have a calculator, that would be your final numeric answer. You would not be expected to go any further than that, but then you would want to include units on it. So if that's f prime, then your units should be units of y, which are degrees Fahrenheit, over units of time, which are minutes, which is what? Fahrenheit per minute. Good. Degrees Fahrenheit per minute. Now, that number should be what, a positive or a negative number? Negative. Look at the graph. It should be positive. The milk's temperature is increasing. So why is there a negative in front of the 30? Because it's supposed to be there. Yep. But that means that the natural log of 0.98 must be what type of number? It must be a negative number, and it is. And let's kind of review that very quickly. The natural log of x looks like this, remember? And it has an x-intercept at 1, 0. So if you take the natural log of any number between 0 and 1, guess what type of number you're going to get? A negative number. You're back. That was a quick conference. Yeah. That's good news, I guess, right? Okay. So that's as far as we would get. We really couldn't even write the sentence because unless we use that number without its negative there. So let's go to the calculator now, or you can just kind of watch. You wouldn't be expected to write the sentence if it wasn't a calculator. But if you did have your calculator and you were curious what it was equal to, you could just now type it in, negative 30 natural log of 0.98. And it comes out to be 0.60, how many decimal places do we report? 3, so 606. 0.606 degrees Fahrenheit per minute. Now we can write the sentence. So let's go ahead and write it. You can write it with me, and we can screenshot it and send it to me for our writing sample of the week if you want to. That'd be great. I haven't asked any other class yet. I was waiting for you all. All right, so in a complete sentence then, like the cold yam, we always start with what? Well, not since. At t equals 0 what? Period? Exclamation point? Minutes, seconds? Minutes. Yeah. If you don't put your units on both your independent and dependent variable, you're not going to get point. So at t equals 0 minutes, comma, you could say the temperature of the milk is increasing, but what word did I use in my sentence? Warming. So try to reuse their wording. The milk is warming, or warming up, whatever you want to say. You don't really need the word up. Is warming by 0.606. Could I get by with saying degrees Fahrenheit / minutes? No, because we need to interpret it in the sentence as units of y over units of x. So by 0.606, let's go ahead and write it out. It's fun. Degrees. Fahrenheit is such a cool name. It has that hidden H in the third letter. Degrees Fahrenheit per, that's P-E-R, not like the cat purr. Like, right? Per minute. Oop, I better write out word minute. Minute. And if I can spell it, M-U-I, menu. Is that minuet or is that minute? Is that minute? Golly. It's at the end of a day on a Monday. Minute. How about that? That is a minute. Minute. Okay. Per. Let's get rid of that. Okay. So if you want, go ahead and leave the equation there and screenshot your words and email it to me. That'd be great. Now, that happens to also be where the milk is warming at the greatest rate. Would you agree? Yes, because if you move that slope to the right, it's going to get flatter and flatter and flatter, approaching 0. And that makes sense, right? Because as soon as you take it out, that's when the temperature difference is the greatest. That's when it has the most to lose, so that's when it will be warming the fastest. Now, one last little thing to this before we move on to the artwork. Let's go back to the beginning here and say, now this was a free response question on a portion of the test where you actually did have your calculator. When you get to part C, you could still do it this way and get full credit. And even though it would be a calculator question, you wouldn't necessarily be expected to give a final answer like 0.606. You could leave it like negative 30 ln of 0.98. But taking the derivative by hand increases the likelihood that you might make a careless mistake or takes up valuable time. So here's all you would have to write if this were truly a calculator question. You always have to signal what you're doing on your calculator. But if you just put big F prime of 0, you know what that means? That means, hey, I'm about to take the derivative of big F and plug in a 0. And how do we do that from the home screen? Math 8. And we'll take the derivative with respect to x. Always x on the calculator because it's a shortcut key. And if you have your equation in y1, you can just recall it. I do not, so I'll just type it in real quickly here. It was 72 minus 30 times 0.98. You don't have to. You certainly could, right? Better to have them and not need them. To the x power, and then the key is over here. We're going to evaluate it at x equals what? 0. And you hit enter, and it gives you the same answer. And so you write that down. 0.606. 0.606 degrees Fahrenheit per minute. And believe it or not, that would get full credit on a calculator portion of a test. So we'll be talking about strategy later on in the year. on an AP exam, if it were a calculator free response question, that'd be all you have to show. They wouldn't really expect you to take the derivative by hand. There's a time to take the derivative by hand. It's called the non-calculator section, right? So there you go. All right, any questions on that? Now, here's what happened several years ago when I first put this picture of this handsome dude in here. As I was walking around, and I didn't walk around today because I didn't get my caffeine, I guess, this morning. But I noticed people were not paying attention to the problem itself, but they were doodling on this guy. He looks very doodlish, doesn't he? He's easy to doodle on. And so I was like, you know what? I'm going to doodle too. And so we all started doodling because we had time to spare, like right now. And then the doodling was just too fantastic. I said, why don't y'all just screenshot it and send it to me? And so I started putting all the doodles into a Word document. And it's only been a few years, since 2014. But now I have a growing collection of cold milk guy doodles. And if you would like to doodle this guy and send them to me, your brother didn't do it, I will add them to the collection. And I do show every class the collection that I've attained so far, minus the ones I've received today, which maybe we'll have those at another private showing later on. But let me show you right now the ones I've received, and the worksheet's due tomorrow for this section, and what else? Oh, be ready for a quiz. Okay, so the first few, they're not good. You know, in 2014, people were modestly doodling because they were supposed to be listening, but now it's like a doodle challenge. So you'll see, like, people are upping the ante. So that's kind of a Kurt Cobain-looking thing, drinking some strawberry quick. And then here's a dude with louver glasses. Here's a unicorn with a creepy phantom white mustache and a polka dot tie. A devilish unicorn. Then you have this one here, that milk stash dough. Those first three were mine, by the way, and I'm a horrible artist. So I was just playing along with the kids. This was Kayla Casberg's right here. Not so bad. Gave him a nice red-headed tint, a little purple earring, and some pink fingernails to match. Then this was Sarah Catherine Stevens. She was in the festive holiday spirit already. Yeah, so that one's cute. That one is downright cute. And the candy cane straw is just a beautiful touch. This one was Erica Pfeiffer. And I totally love his origin symmetric mustache. That is something else. But he's got some piercings going on here and a nice big bow. Like, I could see myself dressing like that. So, anyway. Then you have this guy, Paul Burnett, who he was gangsta. Look at that. That looks kind of like Will Ferrell in that movie, but with some milk, some green milk. I don't know where you get green milk from. Pistachio? I don't know. This was Cole Davis. He was a tennis player. Not much of an artist. But I think this is the one that kind of started the whole creepy clown thing. Right here. Creepy clown. And then this was Jacob Kilford, who sat right behind or in front of Abby Grieve, who was a Montessori dancer. And we put the picture of this and Abby side by side, and some people couldn't tell who was who. It was a striking resemblance. Yeah, she now dances at TCU. This one was Shayna Underwood. Kind of gave him a nice olive in the milk, the goblet. Kind of a nice Greek look there. And this one was Lily House, who kind of kept it simple, the sign of the times, with the cell phone there. Maybe he's taking a selfie. And then this one was Selena Anderson. I think she kind of took the milk getting really hot to heart, and it kind of has like a steamy milk. This guy's giving himself a steamy milk face, bath, whatever. And to me, that just seems like it would clog the pores. I don't know. I don't know if that's supposed to be good for you, but steamy milk. Then you have Austin Schroeder, who, as a junior, asked if you had blood, and he drew some cusps up there. Yeah, that's nice. And then you had Carmen Vega, touch of gray, taking care of his gray hair, kind of creepy. And this one is funny. This is the guy that kind of took it to the whole next level. Andrew Martinez, like, why decorate the guy? Why not do like a Where's Waldo? So, and I had no idea that he was actually there when Da Vinci painted this, but apparently he was on the same side of the table as everyone else. He's right there. Where did this guy come from? I don't know. I thought you invited him. All right, and then he had this here. This is Tinker Bell, Katie Pfeiffer. And then he had Haley Smith doing going Popel there, or Bishopy. Then he had Nakia Cole going with the European influence. And then he had Brent Goodrich, who that was crazy. Just crazy wild stuff. Got some steamy lemonade there. He was still high on his victory of being able to run across the football field in a squirrel suit without getting caught. So, yeah, his mission was done. This one was Colton West as a junior. Went all out here. Took him several days. Finally submitted his 5th draft of this version. This is called a Thirsty, is the name of and you can probably imagine why. Thirsty. So, way to go, Colton. Setting the bar low so that others can succeed. Nick Rainstorff did this one. That one kind of has a pretty cool effect to it. Batman was popular that year. Bat Milk, Dylan Price. Here you had James Hall. Maybe you know him if you're in band, James Hall. That's kind of a distinguished clown right there. Milk, he's saying. Milk. And another Batman by Jair Munoz. Then Austin Burquest. It was kind of around this time, close to Thanksgiving. So, he's catching his own Thanksgiving dinner. Got turkey in his hand and a big old hat. This one here was Ashton Nissen, which, if you look at that picture, to me, every time I see it, I'm reminded of, anyone else see it? Whoopi Goldberg. It looks a lot like Whoopi Goldberg. And, of course, Whoopi Goldberg would be eating special brownies, wouldn't she? Special brownies. So, anyway, yeah. Don't do drugs, guys. Connor Kaufman did the Miley Cyrus thing with the wrecking ball, but still kept the clothes on, thank goodness. Got the suit and tie still. And then Kayla Nash, who could draw horses in 2 seconds with their eyes closed, did this one. And this would be like a good poster to put around campus if we were trying to encourage more unicorns to drink milk. It's amazing. He's got the milk mustache and the amazing holding the glass with the hoof. That's just something else. And then you have the valedictorian, Connor O'Toole, doing Che Guevara, the Cuban revolutionary, but everything goes better with milk, including revolutions. That's pretty cool. The Frozen theme was popular that year. Rhodes Smart, if you know Rhodes, did this one. Kind of has an ethereal, kind of biblical thing. Kind of some blue moo juice there. Grant Gable, Obama. Fit him in there pretty nicely. And then the subtlety of this yellow skull ring right there. Just the only accent he gave him. Kind of interesting. The Milk Elisa. Yep. And the eyes do follow you around everywhere you go. Kind of creepy. And then this one, Jacob Waldman. This one's funnier if you read it. It says, "Want some milk, bro? I got some. I got some. ... I got some." All right, and then Jacob submitted another one. At this point, he was going for quantity over quality. This is another Jacob Waldman. Louvered glasses, pink, cool. And yet, this one was Mackenzie Garner. He stole this milk from this guy over here on the side, which my milk used to look like that all the time because we got Strawberry Quick and Chocolate Quick growing up, the powder. And if you made Chocolate Quick in the pink glass without rinsing it out, it kind of turned to the pink chocolate. So it's kind of good. Y'all ever drink that stuff, the powdered Quick? No? Yeah, it's delicious, isn't it? It's all sugar. Nothing but sugar. Okay, this one was Peter Weibert. Drinking milk is both fun and easy. It's fun and easy. He's drinking a cup of calculus right there. Then you have the Second Amendment. This is James Hall's second effort as a senior. What goes good with lobster? Milk. I heart lobster. Here is Dawson Smith. It's cookie dipping good, Colonel Sanders says. Then you have Brandon Velez, who has all these calculus. Calculus is greater than girls, greater than or equal to. Yeah. He wrote 100 on every single one of his tests that he turned in, just to save me from having to grade it. And he did make 100 on one. But apparently he does that on his college assignments, and professors don't care for that too much. But he came by and visited. Here was Harrison Foltz. Here was Colton West's second effort. Remember, as a junior, Thirsty? He stepped it up here. He literally copied Harrison, but not as well. Yeah, way to go, Colton. And then this is one of my favorites. Austin Moninger took some liberties. Yeah, you don't even really know there's a cold milk guy behind there. But he is. He's there. That's good. That's good. And then Tupac was Austin Schroeder's second effort. Then you got, this was Juan Manrique Buscelli. This was Kayla Thomas. And then this was Megan Reynolds. She didn't turn in the next two assignments because she was working on this constantly. So she took a couple of hits, just to get this one done. But it turned out really, really good. And she hasn't turned in this year's yet because I think she's trying to top herself. But you don't have to spend that much time on it. And then here's some of the ones from this year. Peter Bain sent this one. Don't Drink and Derive. This one is the Joker. Pretty creepy. Then here's Archer. And then another one of those. Here is a wizard with a huge purple hat, oversized. And then here is, this is Jake Abel's Beep, Beep, Good Oil. Kind of funny. Another one. And then here's, you got to see Johann Rossbach. Look at that. That's pretty dang cool. So anyway, have a great day. We'll see y'all tomorrow. Quiz tomorrow. You'll be disappointed if we don't have one.